Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. We are doing lighting optimization right now, and we've got some stuff to do. We have, a mostly working lighting system in terms of how the architecture should go, but we don't really have a solid idea of how we're going to make it run at 60 frames a second, right? We're too slow right now for the size of things that we want to do. And there's a lot of things that we can consider in terms of speeding it up. But at the very least, we should probably finish our spatial hierarchy stuff that we started down. And that is to say that we implemented a spatial hierarchy for accelerating our raycast, but we never really played with it. We haven't even drawn it yet, so we don't even really know how well it's working. We could have like obvious bugs in there, and we'd never know. So our job now is to start taking the lighting system and actually refining it in terms of performance, and then also we need to make the front end to it, which currently just drops down equi-spaced points on our little environment cubes. We need to actually do something more intelligent there, right? We need to have the thing that actually creates the world be smart about where it's going to put down lighting points so that, you can be more reasonably assured that you're going to get decent quality out of the lighting based on what you put into it. So let's go ahead and take a quick look at what I'm talking about here. And again, lighting is one of the hardest things in graphics. It's basically the thing that causes all of the problems. So, you can expect always for it to be a little bit of a struggle. And it's just because it's one of the few things in graphics where everything affects everything else. Obviously, when we talk about the cost of things and how difficult they are to achieve, anything that only involves working with a single thing is usually something we can manage these days. We have a lot of horsepower. So ON problems, like ones that are proportional to their input size, are not that big of a problem. Lighting is not that way. Lighting is everything affects everything else because light bounces off surfaces and hits other surfaces and keeps bouncing and so on. And so it's just a really nasty problem because it's an n squared or worse kind of a problem where you end up with the difficulty of the problem, the amount of work you need to do it correctly, scaling non-linearly. And that's like the worst case, right? Well, non-linear, super linearly. Obviously, sublinearly would be great. So anyway, if you take a look at what we've got here now, you can kind of see that our lighting is working for the most part, meaning that we get predictable results as we move things around. We get bounce lighting, which we want. We keep things relatively smooth. But there's a couple things, like I said, we need to do. One is on the front end. Like you can see, like right now, we don't do lighting translation for our sprites. These sprites are just kind of stamped down here. So only our little actual geometry cubes are getting lit. So that's something that we need to fix. And the other thing is our frame rate's just not good enough, right? And it's especially not good enough when the entire lighting region gets increased over to something like over here, where we've got more things that are being lit. So there's just a bunch of stuff that needs to get sort of improved and smoothed out. So yeah, I don't know exactly what the best approach is, but we've got a couple things to do. The other thing we need to do is we changed a little bit how the renderer was handling submissions of things. And one of the problems that we hadn't actually looked at there is we still did one thing wrong. You can notice we're not getting our clear of the back buffer is not clearing properly because you can see it's black and it's supposed to be the clear color, which is gray actually. So we've got a bunch of things we can work on today after doing the debugging we did on the lighting last week. We've got basically a number of things we've got to do that are not necessarily debugging, but they're like code improvements, code restructuring, optimization, that sort of stuff. And so that's what we need to start working on today. So I'm going to start by saying let's go ahead and try to fix that renderer problem because I don't really want to leave that lying around for too long. It's not the end of the world, but it's just I don't want like bugs lurking in the renderer for too long. We're gonna go through and clean it up once we're totally sure that everything in it is correct. So it's not essential that it be completely squeaky clean, but I don't want it to be too ridiculous. So what you can see here is we've got the render entry begin peels section here. This is when we come through and we do our depth peeling passes, we're gonna render the same information multiple times. And so one thing you'll notice is that each time we go through to clear one of these peels, we end up in a situation where we need to know what to clear it to. And what we want to do is we want to clear any of the peels that we hit. We want to clear them to nothing first, which is, you can see it's 0, 0, 0. Because we want, if there's nothing on that peel, we want it to show through to the peel below it, right? That's the whole point of doing the peeling. And so when we finally get to the bottommost layer, what we're doing is we're clearing that bottommost layer to the clear color, or at least that's what we're supposed to be doing. And since I don't actually have any verification that that's actually happening, I don't know if we're doing it wrong or right or what's happening. So what I want to do is I want to take a look in here and see what's going on with our clear. Do we have something messed up in there? Did we just set the color wrong? You know, I don't know. So I want more information about this problem so I can start to debug it, and that's what I'm going to go look for now. So the first thing I'm going to do is I'm just going to set a breakpoint here. I'm going to turn off, because we don't care how fast this is running, I'm going to turn off optimizations so it's easier to step through the code and we can inspect our variables better. So I'm going to go ahead and look in here. What you can see is when we go to begin the peels, we can see what the peel index is. It's 0 on the first one through, which is what we'd expect. Max render target is 3, which is also what we expect because we have 4 render targets, 0, 1, 2, and 3. So the maximum is 3. We should clear this to 0, and we do. We should clear the next one to 0, and we do. We should clear the next one to 0, and we do. And now this final one should be cleared to the... Okay. Well, there's your problem right there. Here we go. This is our problem. We reset the peel index at the end to 0. And that's because I guess we don't want depth peeling on. So that's our problem. Problem solved. We just need to figure out a way for these loops to work better with each other. So when we hit this right here, render group, entry type, render entry end peels, when we get to the maximum render target index, it looks like... Well, actually, I don't know if I agree with that, because this should have incremented the peel index, and we should have come through here at least one time with the max render target index, right? Because this is only once on peel index is equal to it. So I guess I'm not sure why exactly that happened. That looks to me more reasonable, actually. So what's going on there? Let's take that one more time. I'm not so sure. I mean, I see what caused the bug. We didn't come through here on the final one. But I don't know why we didn't, and that's not great. So I'm going to look at both sides of the loop now to find out what's going on. So I'm going to tag in the watch window on peel index so that I can see exactly what it is at each step. So I started peel 0, I end peel 0, and I increment to peel 1 and jump back. So somehow, when we jumped back, oh, we're not actually entering this. So you see what happened here? This peel header restore that snaps header at. So what we were doing is we wanted to create a loop through our render instructions. And this is the thing that restores the pointer that we're reading from, but we saved the pointer at the wrong time. We saved the pointer, and we really want the pointer to point to the header, right? Not header at. So we really want this. We want the header restore to point to the header we're on so that we run the begin loop again. So does that mean we were never clearing any of those somehow? No, I stepped through it, so how is that possible? That's just very strange. So looking at this here, so it's a little bit wonky. So if you take a look at what happens, we're stepping through the header here by doing an increment of the entry size. But that's a little bit odd, and I'm not sure why we're doing it in that way. I mean, basically what this means is if we wanted to set up the pointer properly for the end of the loop, because this here happens at sort of an odd time, I would almost say I would like to move this out. So the increment, I feel like it might be nicer if it actually happened here, right? Because then the header pointer is still the right pointer to set this to. And that seems more sane to me. Let's find out if I'm right about that. So there's that clear and the increment. Here's the clear again, and the increment, the clear, increment. And there's our clear to the correct color. Off we go. So now we're getting back, we've gotten back to the correct behavior, it looks like to me. So that seems much more sane. Let me make sure, because I don't actually know. I'm going to switch to optimized so we can take a look a little more cleanly here. Yeah, so that's looking more like it. Still get some artifacting there where two things overlap exactly for our depth peeling. But otherwise, we seem okay. All right. So I think that was the only problem. That was the only thing that I was really wanted to make sure was solved, and it is solved. Let's double check also our profile right now so we know where we're at. You can see here, it's exactly what we would expect. Our lighting is taking all of the time, so the entire game is running in very little time, but the lighting is taking forever. And so we essentially know that that's our giant, our big target. That's what we need to focus on and figure out how to, speed up. And so that's what that's what we're gonna look at now. All right, so I'm fine with that. Let's take a look at the current state of our optimized, or our attempts to optimize our lighting. So there's a number of things we want to do here. Some will make things better, some will make things worse, actually. Not just in terms of optimization, but just in terms of the way the algorithm is structured. So we know that basically all of our time is spent inside the, forgot we moved these out, is spent in time inside the lighting propagation, right? So the compute light propagation function, which is this guy right here, is what takes all the time, and it's pretty easy to see why it takes all the time. It's just this giant set of loops, right? Everything multiplies out. So we do a certain number of iterations over a certain number of emitters, over a certain number of rays, each of which then has to loop over all of our collision geometry, or sorry, lighting geometry. And that lighting geometry is broken into spatial hierarchy, but it's still a lot of checking, right? And so loop upon loop upon loop upon loop, each loop just multiplies out the amount of work that has to be done, right? And that just creates a really bad situation. So what we're trying to do here is figure out ways that we can sort of continue to make this more likely to, run in a nice sort of pseudo-fixed amount of time. So one thing that I was going to mention is we never really got our skylight in there. And one of the reasons we don't have the skylight in there is the way that we're currently doing our raycasting is we choose to shoot rays from our emitters outward. And that makes actually pretty good sense at first, meaning when you start, you probably want to do that. But it definitely makes things harder for things like skylight, where you don't really have any particular location that light is coming from. Skylight is something that just kind of radiates inward to everything. And, that's a pretty important component of lighting that, it would be nice if we captured. So we kind of have some issues with that as well, where we don't really know what we don't have a solid plan in here for how we would do that. Obviously, one thing you could do was constantly irradiate everything with skylight. But again, the more you do that, the more extra rays you're casting and blah, 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 blah. So it's hard to say exactly how we want to do that. I'm not sure whether we want to retain an emission-based scheme or not. But my suspicion is what we probably want to do is do something where we have emitters. We do sort of a shoot out from emitters to distribute light from the emission sources. But then we probably also want to do gathers, which we played with a little bit, having emission and gather. We may want to have both happening, again, just because that's probably something that makes a little bit more sense. All right, so the other thing that I'd like to do is point out that I think we're getting pretty low leverage for what we're doing right now, because we recompute the lighting every frame and then blend it with the lighting from the previous frames. And the problem with that is I think we're getting very low leverage from our computation from that. Because once we figure out what the lighting is on a frame, we might as well use that lighting on the next frame and continue to propagate it around, right? I feel like that's the smarter way to do things, where we can basically say, all right, whatever the amount of light we want to keep from frame to frame is, let's just make that be the starting emission for those surfaces, whatever the reduction is, and we'll go from there, right? So that might be the first thing to start with, just so we can get back to something that's properly retaining the actual light and not just blending with the old results. So what I'd like to do is go ahead and take this routine down here. So this is the routine that basically goes through and averages that lighting information. What I'd rather do is have this seed the initial lighting information. So I think we can do that relatively straightforward, actually, by just coming up here and just doing that, right? So right here where I've got this to do, this says reload the previous emission and direction as starting point, that whole situation, right? That's exactly what I want to do here, right? That's exactly what I want to do here. And we can get some nice synergy here, because you can see this box index thing. This is the same loop that we're doing to generate these points to begin with. And so what I can do here is just say, all right, let's go ahead and grab the parts of this that are actually relevant and use those to seed the lighting. So suppose I come in here and say, okay, let's take a look at, and you know what else I can do? Actually, let me do this too as well. Let me save this down here and just nerf it. So if we want to turn the blending back on, we will be able to. Okay, that'll be something we can keep in there. But let's go ahead and grab inside the box index stuff here. I'm going to go ahead and say we're going to load it in that emission. And you know what else too? We don't have to care about this check anymore, because the emission just would be what the emission is, right? So if the emission is 0, it just won't add any emission. So all we're going to do is just add that emission in. And so that's pretty trivial for us to do, right? So all we need is this. Basically, we need to go ahead in here where we set this emit C0. We need to just add into it something like this. So we need to know for the given box what the local index is that we're on, right? And you can kind of see how we were doing that already here. We've got this light index here that's coming off the box light index. If we wanted to know what the local index was off of the box, it would just be the light index minus this box index, right? Which is not something that we currently store, but easily could. So if I take a look at where we're using light index here, you can see that it's really only used in these sort of simplified ways here. And what I can do is I can just change these checks to be a little bit more, well, you know what, why even bother? I'll just do it this way. I'll just reverse compute it here, it's fine. Right? So that's the place in the box where the emission value is actually getting stored. So that would seed the emission for this frame with whatever it was computed to be on the previous frame. And so that is all we want to do there. However, remember, we don't want to use all of it. So we want a retained emission coefficient, because we don't want, we want the old effects to fade over time, right? So we don't know what that efficient could be. It's what that coefficient should be, because again, this is an ad hoc solution. We're we're taking something that we do know how to do, which is slow global illumination, and we're trying to make it fast by making approximations. So this value is literally just whatever will make it look the best, right? And we have no idea what that is, so we'll have to tune it to whatever looks the best. Once we run it, I think then we're done. I don't know that we need anything else to happen here. I could be wrong about that, but we'll find out. Oops, that's not local index, that's light index. And in fact, I can here also say what the local index actually is, because the local index is still a valid name for that. So let me just pull it out here. And that's, I think, all we would have to do to kind of preserve the light so that the light kind of comes through. Granted, that is not a particularly flattering effect for the... Wow, that is pretty interesting. I'm not sure why it's quite so flickery. That was very odd. I think this is correct. And we are retaining a fair bit of the light there. Box storage... you know what? It's not getting written back, though. So the one thing we do have to do is we do need this routine to be still enabled, and we just need the box storage emission to be saved. So you can see that happening here. Oh, and you know what? This normalization also. So, okay. I was a little premature when I said we could nerf that. We can't actually nerf it. The only thing we can really nerf is this, right? We still have to come through here, and we still have to record this information. Although, you know what, actually, we don't even really have to do that. All we have to do is always set valid to false. Because as long as valid is always false, then what it will do is it will always use this branch, which all it does is do direct writebacks, which is what we want, right? No blending, just writebacks. So that should be fine. But yeah, we have to do that final loop because we have to do the normalization of the direction, and we have to store it. So that's all good. So this retains, I guess, too much light, to say the very least, unless I've got a bug there. So let's retain less light than that. We're also getting a lot slower, I think, because there's a lot more surfaces with light on them, if that makes sense. So it's kind of hard to, so we end up doing a lot more propagations in that initial one. But we should also be able to turn down the lighting quite a bit from there. Let me actually see to what extent I can do that. Because now we don't need to do the sort of jacked ray count thing. You know, the ray count gets sort of diminished as we go out here. We don't really have to do that anymore. This can sort of be a flat number that we can tune. Because we don't really have to worry about that initial lighting part of things, right? So I don't know. So yeah, like still like very flickery, right? Unfortunately. And you know, I'm just trying to think through exactly how I want to approach this problem. Because I mean, maybe that's dumb, right? Like maybe you just don't ever want to re-emit values from the previous frame, but it seems like you would want them to be able to propagate over multiple frames, right? That just seems like what you would want to do. For efficacy. But again, I don't really know. These are sort of exercises in figuring out what is the, you know, most palatable choice. So anyway, but looking at this, I'm interested to know what happens if we cast few rays but have a higher retention coefficient. Just want to see what happens here. So you can see what happens when the retention coefficient is high enough. You can see the light kind of spreading. It's interesting, actually. Let me go ahead and change it on the fly. So let's change it down to 0.5. It's really fascinating. But you can definitely see, like, so for example, right underneath, one of the problems that you get if I do this, right, is that because it's not just blending results with other results, you end up in a nasty situation where you still get a lot of flickering because, well, at the stochastic part of the process, which is doing that transmission, is obviously going to introduce the noise, and you don't get a lot of reprieve from that. So if we wanted to do something that's going to be, flicker reducing, what we'd have to do is when we're actually doing, for example, let's suppose we just said, you know what, the light is always going to be, we're always going to propagate the exact same light, and we just want the light to decay more as it goes, right? We could just take more energy out of the system as we're doing bounces, right? And not use as much of it, let the light sort of drain out as part of the bounces and have those bounces affect surfaces less, right? And I'm not sure exactly how we would do that. So, let's suppose we set this to 1. So you just retain all of the light from the previous frame. But when you come in here and, you've got this light retention value, instead of this being power conserving, it will just be power decaying. So for example, when you come through here and we do the retain C minus equals accumulate sample, and we've got the power value in here, right? What we could do is say that power value is actually going to be a lot less than 1.0, right? So the total power that can get distributed out will be much less than that, and the retained light will be much higher. So for example, what we could do is say, well, if we want to do it over 10 frames, we'd say that our power was going to be 1/10 of whatever the amount of power actually distributed was. And so as we come through here, we will retain most of the light that we had at the start. So we won't change our lighting values much. We will just diminish every time we actually transport something by this blend amount, right? And I don't know exactly how we would have to balance this. I'm assuming these should basically be equivalent. We're going to have to work this math out on the blackboard, actually, because I'm not sure. But as you can see, this is starting to be more reasonable. So let's go ahead and say, let's take a look at this. So let's say we did even less than this. And you can see that gets us down to a fairly low amount of flicker, right? It's still not quite as much as we would like, but it's getting lower. And I'm not sure how much flicker we would have if we were to crank our ray count up more. I'm not sure how much flicker we're getting from that could be resolved with denser sampling. Looks like it doesn't help that much. It appears to flicker less just because the frame rate gets lower as we crank that value, but it's still quite a bit of flicker. So let's say we set it down even lower there. I also think maybe we only want to run one iteration of the lighting now. So what I might say is the iteration count, I may actually just nerf this. So we would just run one pass per frame, right? And you can really see, okay, so and this is running at a, obviously also a much higher frame rate, but you can kind of see how it's like, yeah, if we just could get the sampling a little more stable, it starts to be something fairly usable. So I do think, I think that's kind of what I want to look at. I think I want to look at doing something that just does a single pass, so it doesn't iterate. It does a single pass on the lighting, and then it just refines that one every frame, refines the lighting, every frame, and goes from there. So, and the other thing is, I don't know, maybe we change it to being pull-based as well. Because that's flatter. If we go over everything once and pull from neighbors instead of doing push, then it doesn't change based on the lighting environment, the speed of it. It's more stable in terms of frame rate, which I think I also want. So let's just try to simplify this loop down to something that works like this. We're going to run it one time. We're going to run over the collection surfaces. They're going to cast out and see what they hit, and that's all we're going to do. Maybe. And, I'm a little nervous about it because I do think there's a plus to going from the emitters. So we may have to do a distribution pass where surfaces with high emission will get some special treatment where they'll get to shoot rays out as a separate part of the pass. But I don't know. It's pretty hard to say. The other thing to remember is if we add that skylight in there where we're getting light from the sky, that's going to even out the lighting a little bit by giving some some ambient to the lighting that you're getting from the outside, which will also help. But of course, for indoor situations, that's not going to be true. So, your mileage may vary. But anyway, so let's kind of move towards this a little bit and see what we can do. So let's take and look at what maybe this guy right here, and sort of transform this loop into this loop maybe. Also, if we cast from the light points out, that actually might give us a more useful way to sample what lighting we hit. I'm not sure about that, but there's right now we're just, whenever we hit a surface, we give light to the surface point that we were closest to hitting. And what we could do in the future is take light from points that you take lights from all the points that are nearby, much like we do with our interpolation. So I'm not sure, again, exactly how we want to treat that, but I do think that basically doing a collection-based system would be more consistent, just for speed purposes, because the speed will remain the same no matter how much lighting there is going on in the scene. And I'm just afraid that if we go with an emission-based scheme, we're always going to have these nasty spikes in the amount of time that the light takes, whereas as you get more emitters, you get slower, and I don't love that. So I don't know, this may be a big mistake, and I apologize if it is, but I just got to go with my gut on this, because I don't know ahead of time exactly what the right solution is going to be. Right? So let's get rid of these occlusion counts here. Iteration counts. And let's replace it instead with a point collection style scheme. So what we're going to do is we're going to go through each of the points here. And so for every point, we're going to do a collection pass. And this is exactly what we do right here. So we're going to take a sample. This is sample point index, really, where we're going to sample the lighting from. So we'll grab a sample point and a sample direction, and we'll sample the hemisphere out from that direction. And yeah, Once we do that, we're going to want to throw the ray out, and we're going to want to see if it hit. And then from there, we're going to have to decide how we're going to do our transfer, right? So I want to do something like this. We go through everything once. One of the nice things is now emit C1 and emit C0 it's really just a source and a dest, and it only gets used once. So you wouldn't really have to do the write back here at all. We would not have to clear this to 0. Now, that doesn't matter. That's not taking much of the time or anything. So we can retain this, but then when we go to do the final cleaned up version of this, we won't have to do that, right? So this is... So assuming we stick with one pass, we can eventually get rid of this concept, and we can just have a source and a dest. We read from the source, we write to the dest, and we're done. And we don't need to re-clear the dest in any particular way, because it's going to get seeded with the inputs from next time, I think. Again, not 100% sure about that, but I'm pretty sure about that. Yeah, because everything has to come from a lightning box. Those lightning boxes are the things that will be cleared. So yeah, so this will not really have to happen anymore, because the sources will just be correct and the destination will be what we read from at the end, and so everything will be fine. So that's fine. I think that's all good. And then what we want to do now is start to think about how we're actually going to apply the lighting here. So accumulate sample is still, you know, the same thing we want to use. We're just going to want to be passing different information to it. So the sample point that we're going to be talking about, we already know now. So we know it's going to be the sample point normal here is the normal that we're going to get for surface reflection. We also have this decimate C plus closest point index here. I guess that's the target that we're writing to. And so that's, again, just going to be the sample point index. Right? That's what we're writing into. The solution average direction to light plus closest point index, same thing again. This is just the sample point, so that's what we're writing out. And then what we need to know is emit C, the power, and the emit direction. So the emit direction here, this actually isn't going to be negated. It is actually the sample direction. Because again, we're gathering out, not, you know, talking about an inbound point. So I believe that should be sample D, because sample D and sample point arrow N are pointing the same direction, which is what we want for the dot product. And so really it's emit C and power that are the two things we need to be computing here. And those need to be computed based on the box that we hit. Power, probably not, but emit C, definitely. Right? So we got the same sorts of problems we had before, where we got to start thinking about this stuff. That all looks fine to me. So yeah, taking a look at this, we don't care about really how we were doing this before, because we're gonna have to change this stuff. I also want to grab the sky information stuff here. Here we go. And what we can do now is we have a sun direction, a sun color, and a sky color. I don't know why that's like that. I have to change the way these work. So once we have a sky color and a sun color, that means we can also bake whenever we miss. So before, every time we miss, we did nothing. Now anytime we miss, we can use the sky color or the sun color. And we also need, I guess, a ground color, which is something for casting down and don't hit anything. So we kind of just need to know what kind of a situation we're dealing with. I'm going to set this to something sort of a dark brownish color. So this stuff right here will give us the information we need to fill in our missing emissions with something related, right? And so something that does like lighting from the environment. So that'll be nice too, because then we can do this sort of thing we were doing with our sun information here, and we can, yeah, we can basically make a more interesting lighting environment that way. I don't know that we ever have a sun. I guess there's a moon in this game, but it doesn't take place in the daytime, so it's going to be moon color for what it's worth. And probably, I'm guessing the moon is, you know, probably still pretty dark. We're going to have to set these to something reasonable. I don't really know if those are even in the ballpark of correct, but we'll mix the colors later. All right, so getting back to what we need to do here. So this single pass here, where we're just going to do compute light propagation, we're going to do one pass over all of the sample points. We're going to compute the ray casts from each of them, and then we're going to write back. And what we need to do here, sample D in there. Does raycast... So skip index has to be the box that we were coming from. And we don't know the box that we're coming from, which makes it kind of tricky, right? I think we can probably just not bother with that anymore, because we know that we're always sampling from boxes, and we don't check the back faces of the boxes. So I think we're probably fine, at least at the moment, to not do the skip check. The problem is if we want to do something like that in the future, I'm thinking about for bigger boxes. Because if I'm not mistaken, didn't we do something gnarly where we said, like, okay, when we're splitting the boxes and we come through here and build them, didn't we do something weird like negate the radius? Or did we not do that? I guess we actually checked to see if we're inside the box. So I guess we're okay. So I guess we can, if we want to, get rid of this. And we'll be okay. All right. So anyway, in here where we're doing our sampling, we can just get rid of this sample point index. So when we do the raycast, it just doesn't take a skip index anymore. So that's just taken out of the equation. And so, yeah, I think we're left with just how exactly we want to find out what point we're grabbing from once we get array box here. If we don't get array box, then, again, the things we need to set are the emit C and the power. Now, the power, again, I think should be the same. It should just be what it was going to be tuned to before, or, you know, since we don't really know how we want to tune that light retention, we can play with all this stuff later, but it's going to be exactly the same. It's going to be set to some fixed value, and we don't really need to worry ourselves about it other than we need to tune it later. and probably work out some math on the blackboard to figure out what a plausible way of doing it would be. Thankfully, min emission is gone now, so we don't need to tune that. So we're really just looking at some pretty basic tuning here, which is what we want. We want the least number of tuning parameters possible in any algorithm, right? To keep it simple and more likely to be correct. So when we loop over the array indices here, again, we need to know what the emit C is going to be. And so in the case where you don't hit anything, for now we're just going to say that the emit C is going to be the moon color, which is this thing here, right? That's all we need to know. The harder case, in fact, I guess we don't even have to do that. I could just, well, yeah, we kind of do. In fact, we don't need to set that. So what we need to do here now is set this emit C to something in the case of the box, and then we've got all the information that we actually need. So all of this stuff is not necessary anymore, right? We don't care about any of this. We do need to put our sample point in here. We need to grab this. Oops. So we do need to grab the sample point index out, but we don't really care about the rest of this stuff. We just need to know how to grab this thing. We'll talk about that in a second, and what that's supposed to show. Get rid of all of this stuff. And then if we wanted to grab from whatever the closest point is, this would be it. And I guess in here, I'm not really sure how you could end up without a closest point index. I'm not sure why that was being checked. Because if the closest point index, I guess the only case would be if there were no points on the box. But if there's no points on the box, we probably could just if out on that and not have to do this whole thing. But anyway, let's get rid of all this. So really, we're just looking at this scanning process here. And, you know, I guess I'm inclined to say, So let me explain on the blackboard, why I think we maybe want to change the way we're doing that a little bit. So, if we have a surface that we hit, and we know we have some lighting points on that surface, we know we're going to hit in a particular location. And the problem is we have to decide if we hit in a particular location. So before, we're flipping the meaning of this problem around, but the problem remains the same. Previously what we were doing was we were saying we have an emitter, we're going to send a ray out from the emitter, and we're going to see what it hits, and we're going to add light to whatever it hits. So this would be the point we're adding light to, and thus we snapped it to the closest one and added light to that point. That's how we were doing it. We're flipping it around now and saying, okay, now instead what we're doing is we're sampling, right? We're trying to light this surface over here. This is where the light is going. But we're grabbing light from a surface that we hit here. And if we wanted to follow the same procedure, we'd snap to one of the points. Now, why do I think this is maybe not a good idea for our final way to do things? The reason is because if you look at the problems we're going to have with lighting, and the problem we already have with lighting, it's noise, right? It's the flicker. We don't want a lot of flicker in that solution. Where does the flicker come from? Well, the flicker comes from the fact that we have insufficient samples to capture the full lighting function. Now, why? Why do we have insufficient samples? Well, the answer is because the lighting that's incoming at a point is in this really ugly discrete problem where if you shoot rays out along this hemisphere, you don't get a nice smooth curve like this of incoming light. If you did, you could just do a couple samples to find the shape of this curve and then integrate the curve and have the exact answer. The real answer is because all of the surfaces are hard-edged and weird and different surfaces reflect differently, the actual incoming light looks like this, right? It's this horribly ugly super cut, discrete, jumpy, discontinuous function. So it is specifically the discontinuity in the incoming light that creates the flicker, because depending on where we sample, we will think drastically different things about what it looks like. If we only sample here, here, and here, we would think it's this giant incoming bright light thing. If we only sample here, here, and here, we'd think it's really low. If we have a mix of the two, we get more of an average, right? And so every frame when we shoot things out, we get drastically different results in. The only way to really solve the problem is to shoot a lot more rays, which is exactly what offline rendering does. You know, think the pipeline for Blue Sky or Pixar, where they spend several hours rendering a frame potentially or something like this. They can do enough to make sure they get good results, but we can't. We only have a 60th of a second, and we've got a lot of other things to do besides rendering as well, right? So, given that fact, what we need to do is we need to figure out how to make our samples go as far as possible. And so one of the things we want to do is not introduce any more discontinuities than there already might be. And that's exactly what we would be doing if we snap. Because what a snap does is, think about what that means. That means that as rays hit this surface and try to sample the lighting from it, there's basically what's called, and we've never covered this, so forgive me for using the phrase, but if you want to look it up, I'll just mention it. We're basically creating a Voronoi partition of this space. And that Voronoi partition, you could also look at its dual, which is a Delaunay triangulation. These two things are basically the inverse of each other. Well, they're duals. That's a different thing. This is way too much. Forget I said any of that. Basically what we're talking about is, on this surface, we have a set of points, and what we're doing is we're snapping to the closest one. That creates a partition of the space, which is called a Voronoi partition, which basically splits it into this set of shapes, right? Anyone who lands in here will snap to this. Anyone who lands in here will snap to this, and that, right? And thus we have created 4 hard discontinuities along this surface that weren't there to begin with. We've added them. So I think what we want to do instead is take our points and average them together to figure out how much light we're going to grab. And we should probably blend them together based on our distance. So if you land really close to this one, it's this one. But if you land in between the two, it's half and half. If you land in the middle, it's all 4, right? And so I feel like that's a better way of approaching this problem, because now we can say definitively that we have not introduced a discontinuity. We are still left with a ton of discontinuities that are there because of just the surface geometry and how that surface geometry affects the lighting, but we're not introducing artificial discontinuities that will add yet more flicker to a system that already has too much, right? Because we're trying to reduce that flicker. We certainly don't want to do anything that's going to exacerbate that flicker. So I think that's what we want to do. If we get back a box, I think what we want to do is loop over the points of the box in here. And then for each one of these surface points, I think what we want to do is, rather than just doing a check, I think what we want to do is use that closest distance squared as a blend term. So basically take our total distance squared, sum it. So now when we come through here, we know exactly how many, how much total effect we're going to have. And then when we sum our emission up, what we're going to do is say, okay, take the emit C and add the distance squared. We probably want to do an inverse of it, right? Actually. So something that's going to decay as you get further away. So we can do, and in fact, this is exactly what we did before. We can do like 1.0f over 1.0f plus distance squared. So basically, as you get further away, you get lower and lower and lower and lower. So something like this. So we'll sum up those inverse distance squared. We'll use that as a multiplier on the thing that we would have done if we were just taking it just from this point. So the hit points, like so. Oops. So you can see what I'm doing here, right? I'm just going through and saying, all right, where is that point that we hit on the box? And again, we haven't actually pulled out the box values yet, but we will in a second. Take the inverse distance, so we're going to get a thing that falls off. And if you want to know what this looks like, again, you can actually use, nowadays, you can like just ask Google even to graph it. You can say graph 1 over 1 plus x. There you go. So if you take a look at what this looks like, right, I don't know if you can zoom in here. There we go. So we know that this is always going to be, that the distance squared is always going to be 0 or greater, right? So we're going to start right here. We will never be back there. We're going to start right here, and just as we go, we get less and less contribution, right? So as you get out to 1 unit away, you're going to be here. This is distance squared, so 2 is not 2 units away. 2 is if the square was 2 units away. Does that make sense? And off you go. I don't know if you can do this. Okay, so here is what it actually would look like. This is a better graph because this is distance squared. So if this, now this x-axis shows actual distance. So here is 1 unit away, we're at 1, I'm sorry, 0 units away, we're at 1, right? At 1 unit away, and I can, you know what, let me zoom into just the positives since that's all we care about. Can you do, yes, I can. No, I can't. Can I? There we go. There we go. Perfect. Thank you, Google. Okay. So here we are at 1. You can see us fall off. I'm sorry, here at 0, we're at 1. You can see us fall off at 1 unit away. We're going to be at like 0.5, right? You can kind of see, it doesn't unfortunately highlight where it is on this axis, but you can read it up here, I guess, actually. So there's, you can see 0.5. And then when we get to 2 units away, we'll be at 0.2. When we get to 3 units away, we'll be at 0.1. 4 units away, 0.05. So you can see it's just a smooth fall off curve. The only reason I'm using this right now, we haven't done any analysis or anything on it. The only reason I'm using it is a convenient function to start with for just fall off that doesn't need to be checked, right? Meaning I don't have to check to see if the value is 0 first, which I would have to do if I just did 1 over the actual value. So 1 plus the value here is preventing me from ever having to check whether it's 0, because I know it can be 0. I could be right on the point, or at least very close to it, and then my function would explode, and I don't want that. So I want this is well behaved everywhere we care about, right? So there's a way to get an inverse distance on there, and then when we do the total distance, and you know, I might change this because it's not really total distance squared. Really what it is total weight. It's the total amount that we've added in, right? So we're going to go through, we're going to sum up this total weight, and in addition, we're also going to take that Handmade product like we were doing before to produce exactly what we think this point should contribute, and that's going to be our emit C value. Once we have our emit C value at the end, now we know this was a summation of various weights. We don't know how much weight in toto we summed. So what we need to do is now normalize both values up. So here is the one place I will have to check if total weight is greater than 0. Now total weight will always be greater than 0 if we had any points at all. But I'm just checking to make sure that we do have some points, right? Because maybe we put in boxes that don't have any points in the future. So, you know, that's all. So then what we can do is we can produce im total weight. That's just 1 over the total weight. And now we can normalize everything out. So now we can do a Handmade product. Or actually, I guess we can do emit C. It's not a Handmade product, just a regular scalar product. We can multiply the emit C by it. And that will tell us exactly what our emission color should be, averaged based on distance from the points that were involved. Now, there's one nasty part of this. And in fact, I guess this is... Yeah. I would like to do this with only one loop, but I'm not sure how I could. Because in order to know how much light I'm taking away, I need to know what the distribution of energy that I'm taking away from each point is. And so in order to do that, I need two loops. One to figure out what the total weight is, and then one to actually apply it. And that's kind of ugly, but I'm not sure any other way to do it, right? So I don't really know if there's any way around that. I mean, I guess we'll have to find out how bad it really is to do the loop twice. It just seems nasty. I don't even like doing the loop once. It's not fantastic. So doing the loop twice seems like really not fantastic. But I just don't see any other way you could really do it. You could fake it and say that you just take the same amount of light from each of them, even though you aren't doing that. So, you could say, this is the total amount of light I'm going to take. I take it evenly distributed across all of them, even though that is not how much light I actually gathered from each of them. So it's an approximation that could have deleterious consequences. It could add or remove light from your system in potentially a bad way, And one of the problems, I guess, is that it's just really hard to say. So probably what I should do is do the two loops first. Right? And then back off from the two loops as much as I can in the end. I'm not sure really any other way I could do it. Because, it's just like if you want to do a scattered point interpolation like that, I don't know that there's a lot you can do to prevent the double summation. Yeah, I mean, or at least I'm not able to think of what it would be. Let's put it that way. So I don't know. Sorry. So this is a tricky bit, and I'm not sure how exactly we're going to deal with it in the end. But we'll start with this and we'll go from there. So if we come through here, we'd have to do this twice, and then we would have to do something smart about it. I suppose what that does mean is if we were going to do it twice, we could avoid having to do this actual extra inversion here, because we could just pre-invert the value and multiply it through on the second pass through the loop. So if we do end up having to do two loops, I guess we can make them slightly more efficient, and that's slightly good, but not that good. So certainly not as good as not doing two loops. So let's finish off what we're doing here. Let me go ahead and grab the information we actually need from this. So inside the ray box stuff, we want to figure out which box we hit. In fact, I guess we could just do this. If there is a hitbox, then we need to grab out the starting hit index there. And we need to know how many points there are. These are both exactly what we want to do here, so that's all good. We don't need these two, but we do need the ray position. So we need to compute that by stepping out along it. After we do that, we can do this loop properly, and that value will be correct. We can also do it again down here in the nicely piggy way. And then, but we, once we get down here, the thing that we really need to do is take that emission that, that new emission that we're creating. We need to remove some of that light from the result. And so that's the next part that we have to do. And so we'll figure out how we're going to do that in a second. Once we finish that, then we really are ready to do the emit C, so we can finish accumulating the sample and everything's happy. All right. Yeah, and off we go. All right, so let's take a look at how this is working. We start out with our compute light propagation. Off we go here. And we're going to accumulate into the dest emission values all of the light that we gather. And the only thing that we haven't done yet is in here, we need a way to record the fact that some of the emission got nerfed, right? This can't happen in line, actually, so we can get rid of that. This has to happen at the end. So when we do our final loop over all of the points, this is the place where we can actually reset the values. So yeah, inside here, yeah, we can reset these. Now, I don't know, we may at the moment actually want to do these here. This way we always process every point. And so this will do that sort of final push to get everything out of the destination and clear the destination. And again, we can probably clean all of this stuff up once we know exactly how everything's working, because we can structure our buffers properly to not do any extra clearing or any extra anything that we don't need to do. So looking at this here, when we do this pass through, what we should be able to do is say, well, however much we wanted to remove from any given point, what we should be able to do is now say, well, whatever the dest emission value for this point was, we should be able to remove as much of the power as we wanted to from there, right? So we're going to do something like this, where into the dest emit C, we record the fact that we've taken power out. And we'll make sure we can never take out more power than we had to begin with, just to make sure it never goes negative. So in here, we know which one this is. This is the hit point index. And what we want to do is, since we know we took power out of it here, and we know exactly how much power we took out, yeah, we should be able to do the exact right amount of output power. So if the amount of power that we're taking out is this power value, then how much we would normally take out is just the power times that, right? Like this. But we know that we're not using all the power. So what we're actually doing is we're taking the inverse total weight here, and I'm going to go ahead and do it like this. We're going to need the inverse total weight to normalize our inverse distance squared, and that's going to give us the modification for the power. So we'll take the power, we want to multiply it by our contribution, which is the inverse distance squared, and then normalize by the inverse total weight, right? So this says however much power we were going to use, total, which is just prescribed, however much power we want to remove on a particular sample, we will then use our distance squared as the weighting value, our inverse distance squared as the weighting value. And then we'll effectively divide that by the total weight we know is there. So that way we take the fractional part of the power that we're responsible for, and we only remove that much power from the destination. So I believe that's correct. We got a couple things we got to do here. So the ray point, this emit P. So the ray is going to be the sample direction. Oops. Sample direction and the sample point P. There we go. The moon color, we just want the RGB part of that. Retained C, this is really not relevant, I guess. Although I suppose, what was that actually doing? This was taking that fall off into account as well. I don't know that we really want to do that. Like, I'm not sure we really want to do this anymore. This tells us the total amount of light that came back. So we could, if we wanted to, do it after the fact and actually remove the correct amount of power based on how much we used. But I'm not so sure that that makes sense, because I don't know that the amount that we actually transfer here is related to how much it should be giving off, because it depends on how you look at it. The light gets emitted one way or the other. So yeah, but you know what? Since we did it that way before, I'll keep doing it that way for now. If we do want to do that, all we'd have to do is just this. So if you take a look at what's going on here, this information, right, all has to come from the hitbox stuff. We could actually do this all in line. We don't even really need to do much in the if statement if we don't want to. So what we could do is say, okay, this box, this whole thing here with the hit index and the hit point count, I think we should be able to do this like this. Right? So if we look at what's going on here, excuse me, we should be able to do a thing where we just keep most things happening exactly the same, like so. Yeah, like all of this stuff can be exactly the same effectively. And then when we get down here, hit point count will be 0, so we will never enter these loops. In the case where we didn't hit a box. But everything else will proceed exactly the same. So then when we figure out how much point light we use there, right? So we accumulate sample, we get back our used C. Now we just know it's actually just that amount of the used light would come out here, right? Now, the reason that I'm just not sure about that is because now the color, yeah, see, that's just not going to work because the color is going to be wrong. It's since the color is a blend of the multiple points. Yeah, we can't keep doing it that way. So since we're using a blend, we're gonna have to stick with a way that doesn't require us to do that, right? So I think we're gonna have to just nerf this concept because once we blend the colors together, we can't keep them conserved because we wouldn't know exactly how to reapportion that information. So I think we do have to do it exactly this way, and this information just has to go away, unfortunately. That's just how that has to go. And that's okay. Again, this is all approximate, so I don't think we don't need to perfectly conserve the energy in this system at all. All right. So when we come on the outside of this loop, I guess I'm going to do it. I think I might want to do it like this. Let's see. Yeah, iteration count not happening anymore, and it's not showing up there. All right, so now we just have to debug this, which is not going to be fun, obviously. And yeah, that's not a great start. As you'll notice, we get no lighting at all. All right, so let's go ahead and start stepping through. On the plus side, you will notice really great frame rate when you don't have any lighting, as it turns out. Oh, it's not no lighting. There's a little bit of gray in there. So I take it back. It's not quite no lighting. It's very, very little lighting. So let's go ahead and step through that. And I'm going to just basically walk myself through that sort of new structure for the routine and see how we go. All right, so here we are. We're going to go over these sample points. Take a look at it here. So you can see there's the location sample point. There's the color that it's reflecting. And here's the normal. I don't think next free is ever used anymore, is it? Actually? Yeah, I don't think so. So let's just get rid of it. So in we go. Here is our sample point. We are going to take a random ray direction. And that should be pointing in the same direction as this is, which it sort of is. It's a pretty angled... that's a pretty steep angle to it, but, you know, certainly still correct. And then we're going to go ahead and do our ray cast. Here's the ray information we got back. There was a box that it did hit. Here's the information for that box. So when we come in here, we should enter this loop, and we do. And so now we're going to take a look at what our first point index is for this box. There should be 4, and there are, and it starts at that one. We're going to take, again, our sample point, and we're going to add however far we went along this ray, which was 2.7 meters here. along that ray. And again, that sample direction is normalized, so that's exactly how far it should go. We then have a total weight value here. At least I assume it's normalized. We have a total weight value here that we initialize to 0, and we're going to sum. We loop over the surface points, and we get the distance squared to them. That's how far away we are from that one. So its inverse distance squared is 0.8 there. And so we sum up the 0.8. And then we do, using that as a weighting factor, we take the reflected value and the source emission here, which let's find out what that actually is. So this point source, it doesn't give off any light at all. Which I suppose would be true for most of these. So, you know, what we may be seeing here is just the fact that we're too undersampled to pick up because we're not going from light sources, as with before. Again, I don't know if we need an initial seed pass on the light sources to get the lighting out into the environment, but no, actually that can't be true because we should be picking up moonlight. So I think we've got just a bug in general. Anyway, so if we take the total weight that we picked up there, that's a reasonable value for that to be taking. The inverse total weight should be the opposite of that. And it is. So then we go over the surface points here, and we just decrease their power, right? The power value is very, very low. I feel like maybe we just need that power value to not be quite so low. That's kind of way too low. Yeah, let me go ahead and also the moon color is never actually getting multiplied by the, oh no, it does get modified the power there. Yeah, I think that power value is just way too low. I don't know how we would ever accumulate anything with that. I guess the previous one, because it was transmission based, is not quite the same, but yeah. So I think here the power, is just going to be, I don't think light retention gets used anywhere else. So I think all we really want to do is just say something like this. Right? And I don't know what those values want to be tuned to yet, but we'll have to see. So still really problematic in terms of the sampling. I'm not sure what's going on there. It almost looks like it doesn't retain from frame to frame to me. I wonder if we just have a bug in how we're doing our retention there. Let me just double check something here. Let's make it go really slowly. Oh, right. Okay. We gotta fix that. We gotta clean up the game code one of these days. I keep putting it off. Because, well, it's game code, not engine code. But, let me just take a look at what happens here with a lot of rays. Yeah, so something's kind of weird. So I'm doing something definitely wrong. That's not just because of the inbound versus outbound lighting. So something's up, and I'm not sure exactly what it is. So let's double check this again. Okay. Oh, yeah. It's quite obvious, actually. So we're never actually summing forward the destination's emission. So yeah, we weren't propagating forwards at all, in fact. So in order to start with, every point has to get its emission from the last frame added into its destination in order for it to persist the next round. So yeah, that was just dumb. So we were effectively getting no benefit from the actual previous round. It was just purely the original sampling, right? So now I should be able to set this down back to where it was, and we should be able to see sort of more where we're at correctly. With the lower sampling rate here. There we go. So yeah, so you can see first of all is we do, now that we've got moonlight in there, you can see you get flicker from the fact that, you know, the moonlight samples are kind of unpredictable. And the blend amount also is set, you know, pretty randomly now too. We could see what happens if we smooth quite a bit more. And it reduces the lighting quite a bit, but doesn't really reduce the flicker enough. So I feel like we're still kind of not handling that properly, right? It seems like the flicker stays the same regardless of the blend amount. It's just the brightness, right? That's pretty awesome. If you get enough light in there, you never get rid of it. So yeah, I am actually relatively optimistic about this. Again, we're still going to have to fight this flicker quite a bit, but we're getting closer. All right. So yeah, what we want to do now is start to focus on how we can, keep our sampling to something that's going to be more consistent. Obviously, one way is to increase our sample count, but it seems like maybe we've got other sources of flicker. I'm not entirely sure, because it didn't seem like increasing the sample count reduced the flicker as much as I would have expected it to do. 4 is a very low number, and when we increased it to 64, I don't remember seeing particularly great improvements in the flicker. Right? So maybe what we want to do here is say, okay, in this case here, we're keeping the same. Here's the thing that doesn't make a lot of sense to me. So we're keeping however much of what we had last frame, right? So if I set the blend amount to 0, oops, it should stay the same. I guess we don't want to do that right off the bat, but if I change in the middle of the lighting solution, right? So let's just say we get a lighting solution. The first thing we should verify is that if I actually go through here and pick a particular spot, if I come back and I change the blend amount to 0, I should get a frozen light. And I don't. So something weird is happening here, right? Because if I literally can't transfer any power away, something's busted. I mean, this value should always be 0, so I'm not sure how the destination emission can ever get to be anything else. Oh, you know what? Retained emission coefficient is exactly what's happening there. So let's say the retained emission coefficient is always 1. So we keep everything undecaying. In theory now, right? If I come down here, let's turn it on. Also, it doesn't actually need to be doing that weird large one, right? So here is a retained power of 1, so there's no decay factor at all, and it's kind of spreads out ad infinitum, which so I guess in terms of decay here, we want the decay to come from this loop. Now let me just go ahead and really quickly, I guess it's the skylight too that always, because the skylight is always adding power to the system, right? I mean, I don't know, let's take that out of the equation for the time being. So here's no skylight. Right? So now in theory, if I go ahead and turn off the power transmission, I should get no change in the lighting. It should just be the same, which looks like it is. And then when I turn it back on, I should get transmission. Here's lesser transmission. All right. So at least we know that's correct there. So the thing that I'm focused on that I think I still have kind of a buggy approach to here is that I feel like as the blend amount goes down, the flicker should go down. But that's not really what's going on. I'm still seeing a ton of flicker, even if the blend amount is 1/100th of the total light transmission. And moonlight is off. Right? So something's busted about how this is working. I'm not thinking about the problem correctly, because that should just not be the case. So let's take a look at a couple different things here. We know the destination emit C will always be 0, 0, 0 at the start. We know that we come through the loop, we will, for each sample point, we will start out by initializing its destination, its output emission to be whatever its input emission was. And that seems good. And of course, we won't overwrite any transmission that already happened if it got transmitted from a point prior that happened earlier in the loop. As we come through here, we're going to take a weighted average of these points to create our emission value. And the amount that we're going to add for light into the system is going to be the power, right? Because we're going to do that inside accumulate sample here. I don't know why we're using the length of the light color. Oh, because we are trying, yeah, never mind. That's just trying to figure out for the average direction of light. So we're going to use whatever the power was times the light color. And we're just using the angular fall-off factor there. So we should be adding less light to the system than we're taking away. Because the angular fall-off, right, should be taking light away from the system. So what I'm seeing happen is the exact opposite of what I would expect. So I know we've got a bug in here somewhere. Because that can't be correct, right? That just can't be the case. There shouldn't be any way for it to be getting brighter over time. It should be getting dimmer over time. But again, I really don't see it. I guess let's double check here. Let me make sure that we're summing these exactly the same way. So in here where we do our emit C, I'm just going to take this power, right? If we were to sum it exactly, and we could take, if we look here, we know that this power is going to multiply the emit C here. We can just say, all right, the emit C here's our weight. It's going to be the inverse distance squared times the inverse total weight. We can even assert that the weight is less than 1. And I mean, we may have to put an epsilon in there, but we'll see. And then what we can do is say, all right, we're going to reduce it by the power times the weight, and we're going to increase the emit C by the weight. We even know that the contrib color is the same in both cases. It's this. So that's how much we're contributing. We're going to remove that amount of light from the surface we took it from, and we're going to put that into the amount that we're about to distribute. We don't multiply it by the power because it's going to get multiplied by the power down here. I don't expect that to do anything different, but I just wanted to sum them in the same place using the same values just to keep things a little clearer. And it's really not, right? That's exactly what it was doing before, right? So we have to figure out why this is producing such a drastic difference. And so what I'm going to do here is I'm going to take a look at a couple things. First thing I'm going to do is I just want to step through this and see what this comes out to be. So the weight values are all, this assertion is not firing. So we know that the weight values are all exactly as we would expect, you know? And the, yeah, just want to make sure I was in debug mode there so I can look at everything. And so if I take a look at what's actually happening here. It all looks exactly right to me. I don't know why I can't step into accumulate sample. Did this not recompile or something? Why was it moving? Why is it moving that down there? There we go. All right. So if I take a look at what's happening with the, with the Destimit-C additions here, I mean, they're just, that power value is so tiny, right? Basically, something's up. I kind of want to measure the total light removed and the total light distributed, right? So if I was to take, these two, I guess I can just reinstate this temporarily. Or I should say total added, total removed. So if I just measure these two together, right, the total amount of light that we add to the system at any given time is going to be this. And the total amount removed is going to be this. So yeah, you start with the same light you assume you end with the same light you started with, and then this is the thing that determines the balance, right? So whatever you did in here and whatever you did in here, those two things, they're if total removed is more than total added, you should get dimmer. If the opposite is true, you'll get brighter. So I'm just curious, I want to see now what those values look like over time. And so those values look exactly like what I would expect them to look like. The total amount of light removed is always greater than the total amount of light added. And so I would have thought that we would get the opposite result from what we were seeing, right? Because of the angular fall off involved, I would have expected I don't understand how it's getting brighter. And now we have like numerical proof that the thing that I'm assuming should be happening is what it thinks is happening as well. So there is some bug in how we're doing this computation, and I just don't know where it is. But that's our job. We got to find that. Because you can see this is not getting dimmer over time, it's getting brighter over time. Like, you can see that happening very clearly. Right? And yet, the opposite should be true. Now, I guess technically, maybe I'm looking at this the wrong way. Technically, we do add light to the system, though, because we do add the actual lights themselves. So I guess what we could say is that because we're adding those lights themselves, maybe that's enough to tilt the balance in favor of light always. I mean, that certainly seems possible. And, you know, if you just don't have quite the amount of sync. But, I mean, it still seems like an awfully fast spread rate for such a small blend amount. Like, what happens if it's just ridiculously low? And so you can see that even when the blending is incredibly slow, you still get a very high flicker rate. Right? Which is totally wrong. Because if the only way that something can change is by getting samples from this small of a coefficient, how is it possibly flickering? It should not be able to change how much light it has by very much at all on any given frame. It should be almost impossible, right, to affect any change. So the fact that we're getting such an obvious flicker, even at such a small frame rate, suggests to me that something pretty majorly wrong is happening with how I'm doing this, and I just don't know what it is. But I'm going to have to figure out a creative way to look at it. And again, I thought, and I mean, we'll re-verify it, but I also thought that we have no flicker, nothing changes, if I just take a particular state of the lighting system and turn the blend equation to 0. And I guess, you know what, I can go back to real time now. Right, so, you know, flickering like crazy, right? Just absolutely nuts how much flickering, despite the fact that it's supposed to not be able to change hardly at all. If I go ahead and change the blend amount to 0, and I mean, the nuts thing about that is look at what happened instantaneously. These went from red to black. Even weirder. So I think this flicker is coming from a bug in terms of how we're treating the lights on output and not from anything else. Because when you can only change the lighting by that much every frame per ray, and you're only casting 4 rays, I mean, it should be impossible to get flicker. It should be almost impossible to get flicker. Even if lights were 1,000 bright, they could only affect the RGB color by one, like, by 1/100th of its brightness in a perfect scenario. If all 4 rays hit 1,000 bright light. And that's just not common. That's just not the common case. So let's double check our assumptions. Maybe something outside the loop is screwing us up. So let's take a look here. When we're coming through for outputting the results of the lighting here, you can see me going through, and we're never going to hit this case anymore because valid is always equal to false. So we're always going to come through here. And for each point, we're going to copy back the emit C0 into the permanent storage. And we're going to take the direction and we're going to normalize it. Which makes sense, right? That's what we want to do. It could be that that average direction to light is what's flickering. You know what? Maybe that's what's happening. Maybe because we don't know what the average direction to the light is. Yeah. That's what's happening. Because we don't know what the average direction of the light is, if it's 0, we will get no lighting. So that's the flicker. It's coming from the average direction to the light not being set. So if instead, when we seed our lighting, we also seeded our average direction to light here, I bet our problem goes away. Right? So here where we take our light in, like so, I'm going to go ahead and also take the average direction to light in as well. So we'll seed with that initial value. And let's see what that does to the situation. So now I'm still getting a ton of flicker there. Did I do that right? Average direction to light, light index equals box storage. Local index direction. What do we do with that? We clear it. That's no good. So I did absolutely nothing with that. Try that one more time. There we go. Now that's what I was expecting. Okay. Finally got to the bottom of it. Now, let's try a more reasonable blend amount. Much better. And finally, now we need to work on our transmission amount. This is the light retention factor here. So what I think we want to do is, again, you know, I don't know how much light we want to remove per frame. I'm not sure exactly how we want to do this. We got to work on how we want to do this. This may require the blackboard. This might be tomorrow's job. Because you can see we get a lot of flicker if we have something in that actually decays. So I'm going to go ahead and say let's get rid of the retained emission coefficient there. Copy those two pieces of information out. There we go. And furthermore, one of the nasty problems about this is we also need to know how much we want to weight this average direction to light here. So that's a little bit hard to say as well, but hopefully that will not be too much a big deal. We also don't know that we ever really want to use the average direction of light. We may just decide that that's a dumb thing and we should get rid of it. But so you can see that we're getting a little bit too much instant popping of light as it comes in there. So there's something still a little busted with how we're doing our transmission here. That power, the blend amount power, it's seems to be much too powerful, and I'm not sure why. So our emit C is somehow much too large, even though it should be quite a bit lower. and I don't know why that is. Now, that could be because the max light value is too high, and so we're just transmitting way too much light. It's hard to say. Yeah, I feel like we're gonna have to do some blackboarding on this because I'm kind of now just tweaking a value for no apparent reason, and we kind of want to make sure we know what's going on with that, right? So there's clearly a balance here, and it seems like light is never getting removed at the system in a sufficient amount compared to how much is getting put in, which is kind of odd as well. So if you take a look at max light emission here, for example, you know, I wonder if this is really the thing that wants to be coefficiented. Like how much light you put in the system is a little bit more conserved. So the amount you preserve is the part that's kept up, and the part that you put in is much less. Still looks like that's always going to add light, though. You can see it's always adding light to the system no matter how low we make that value. So yeah, we're getting closer, though. What time is it? We got 4 minutes left. All right, I'm going to call it there because we got rid of one of our major bugs and we rewrote this routine to work more properly. So what I'm going to say is we just now need to work on our light power distribution, how we're going to decay and how we're going to make sure it propagates fast enough. I think we're getting close, though. I think we're getting close. What I might say is, like, let's say, you know, as just an example test here, suppose we did emit C, this part here where we do a remove C. Suppose we always remove, you know, removal ratio or something like this. Suppose we had a thing here where we could remove a certain amount of power on bounces. And so our removal ratio, you know, is going to be higher. Like, for example, we don't really want this to go negative. So we would probably have to threshold it. But basically this part right here we'll just clamp. So at the end here we'll say can we do a whole vector clamp here? I just want to check if it's greater than 0. So let's do it this way. So something like this. So that way I can make the removal ratio be something higher. So we can remove twice as much light as we tried to add, even on top of the previous part, right? It's so weird that that still doesn't seem to be enough. I feel like there's maybe one more bug in here. Okay, it's gotta be the case that we've got a bug where we're just not removing light. Like, it just looks like the light never really gets removed. I'm just going nuts with this value now just to see. So I can crank it high enough to make it so that it kills any transmission. All right. Super weird. All right, so basically we've got some weird stuff going on here, and we're gonna have to debug this tomorrow. So that'll be our job tomorrow, is to figure out how to get the light balance to be correct, because it's not correct at the moment. Something definitely is odd there. Let's go ahead and go to the Q&A. I'll be pretty interested to see exactly what's going on with that light. It's interesting. It always seems to retain a fair bit of it. There's still one more thing in there that I just don't get. It's kind of cool what's happening right now, but totally not. It's totally a bug. Hengo, I don't think your early approach, kind of like photon mapping, but weird, will work. I think it's worth rethinking. Well, we've rethought it a couple times, so I'm totally not adverse to it. However, I'm not sure I'm ready to say that it won't work yet. It would help if you said why you don't think it will work also, so we could discuss that. Doesn't surface need a hit to have its light reduced? If nothing hits the surface, the light will remain constant. Yes, which I think is okay. Actually, so you know what's interesting is actually this should be bidirectional too, shouldn't it? Like when you have a ray between two of them, they should transfer light between each other, technically. This is running on only one core of the CPU, by the way. So when we actually see, if we multi-thread it on the CPU side, or move it to GPU, it would run very, very fast compared to what's running now. NU NF wait emit C plus equals wait times contrib C. No, I think that's correct. That's what I intended anyway. What are you using? Forcoder. Is the RPI still a thing? What is the RPI? It's interesting. Yeah, I was just thinking about the bidirectional nature of this. So when you hit something, you should transfer light between the two of you, technically. You know what? And also, there's another aspect of it, is when you're transferring light, because you're using the previous lighting to do the transfer, you also, it's unclear whether it's correct to not use the same array. Because sampling from the previous light solution is going to allow you to multiply use the amount of light coming from any given source, right? So if you take a look at this, it's really not correct to have to do a previous and a next. You pretty much need to make it so that as you do hits, you are moving the light around that you have. But yeah. Hengo, this is radiosity. That's what we're doing. The previous loop was more like radiosity because it goes from emitters out, which is the traditional, well, there's both kinds of radiosity, right? But this is literally radiosity. So the thing you just told me to Google is what we've been doing. So yeah, it's not over the top for a live game. It's what live games do. Granted, they're not 2D games. They're usually full 3D games, but. Does anyone know what the RPI thing was? Are we still... I just need to know what acronym RPI is referring to here, because I'm not sure what the question was. Oh, Raspberry Pi. Yeah, I mean, definitely at some point when we're done, we'll port to Raspberry Pi, whichever incarnation is popular at that time. We will have to turn off a bunch of graphics features for that, because the Raspberry Pi just doesn't have much in the way of graphics horsepower. So, like, we won't be able to use full lighting or any of that stuff on a Raspberry Pi. But we'll be able to run the game part of the game just fine, and we'll have a reduced, unlit version, let's say, at not not 1080p and not lit, but, the rest of the game will be fine. All right, so I think that's end of queue. So tomorrow I'm going to try making this bi-directional, and I'm using one array. I think that's what I'd like to try, and we'll see how that goes. Again, just in case, since there was some confusion, this is absolutely how radiosity works. This is exactly how radiosity works. You can even literally look at the previous loop was like straight out of radiosity. I'll show you what I mean. Let's see where we get sampling approaches, right? So here you go. So this is what we're talking about right here, a sampling method for, without having to update everything at once. And they're the predominantly ones that are predominantly used for obvious reasons. And what you can sort of see is this is exactly what we're doing, right? We have a path tracing program that uses the paths that it ends up with to transfer light between two surfaces. And there's a shooting-based schemes is more specifically what we're talking about, right? In the previous loop. And a gather-based scheme is what we have now. So like a shooting-based scheme, which this page is not very good because it's asking you to look at something else. There's probably a better page that you could look for if you wanted to know. I don't know if this is good or not. But like the previous one was a shooting-based scheme because it basically starts at the emitters and looks outward, right? And the new one is more of a gather-based scheme because it starts at the receiver and works outwards. But what I was just realizing is we might as well just do it bidirectional because everyone in this case is both an emitter and a receiver, so there's really no reason to do them separately like that. So yeah. So yeah, just to be clear again, since there was some confusion there, this is absolutely radiosity. There's no other description for it. It ain't photon mapping because photon mapping is, although they're similar because they're both path tracing based, right? Photon mapping just basically says, I'm going to start at the emitter. I'm going to shoot photons from the emitter as particles. Every time they hit a surface, I'm going to either decide to keep the particle on the surface or resend it. And then at the end, I just take the total number of particles on every surface, and that's my brightness, right? And that's not what we're doing here. Again, the difference between radiosity and photon tracing is actually very small. But keeping the transfer between surfaces and the total number of light on the surfaces as actual values is what makes something more like radiosity, whereas just treating it as a single set of particle shots is what makes it more like photon tracing. But thinking of them as two different techniques is really not correct. They're very similar. I thought radiosity approximates the light for one area and not trace single race areas. No, so radiosity can be implemented in multiple ways. So there are radiosity techniques that just do an n-squared pass over all the surfaces and try to solve in a giant, in one giant solve, try to figure out how the light will normalize. That is not the common way to do it anymore because it's intractable in a lot of cases. So the common way to do it now is iterative with sampling-based approaches. So you basically just count that you try to structure your solver so that as you sample, you converge on a valid result, right? In game development, it becomes, difficult because you don't have a lot of time. So you tend to spread it out over multiple frames, but it's the same basic idea. Karish Cross says, McGuire's 2016 paper, Deep G Buffer for Stable Global Illumination, has a very good implementation of radiosity, and his implementation of a Deep G Buffer is analogous to the depth peeling you were using in Handmade Hero. Oh, that sounds pretty good. I have not seen this paper. Maybe we should look at it. So it looks like they do... That's interesting. I'm not sure we really want to go this route because this is entirely screen space, even though it's depth peeled. That might be fine for us, though. I mean, it's hard to say. I'll have to read it in more detail. And they do keep it from frame to frame, just like we are. Are we implementing transparency? Yes, we do transparency to a limited extent. Like, you can't stack up an infinite number of things. You can stack up, like, one or two things. Right. That's already happening. In fact, did we turn off the particles? Let me turn back on the particles. So you can see although these guys fall through the floor since they don't bounce at the moment, you can see that these guys are actually transparent, right? And they fade out. I think that's the only objects in the world that we have that are transparent at the moment. That's transparent right there, obviously. It gets transparent, it gets close to the camera, so there's a transparent surface as well. The depth peeling just handles that. And when you remove the light of the current frame, remove C after, say, 5 frames, you have to in some way clear dest C and add only source C and restart the blend, otherwise it will add forever. Very small portions will get added constantly. Did I misunderstand something? So, in theory, anyway, I guess what I say is, I don't know, there may be a bug in it. So we'll start with that. But in theory, anyway, we're adding light to the scene every frame because the lights themselves are getting added in. So it is true that we add light, and that is something we have to account for. But we also remove light every frame by the fact that angular fall off is not accounted for. So we're removing about twice as much light per frame as we're removing. The amount of light that's transported per frame is about half as much as the amount we take out. Yet that's still not enough to balance out the fact that we're adding light every frame, apparently. Although we could also just have a bug. So I really want to make sure that we don't have a bug first, if that makes sense. But yeah, and the other thing I'd like to do is switch to using just one array, because I feel like that's another source of problems. Because basically, when we create the new array, we have sampled from the old array. So here's this. Do you want to hear a really dumb idea? I have a dumb idea. Just bear with me for 1 second. I was just thinking of a really stupid idea that I want to try. So one thing we could say is, what if we just said the total amount of light has to be constant? Right? What if we just said that? So what if we just said, okay, when we start, we're just going to assume that we have a total light value. And every time we come through here, we're going to say that the total light is going to be, you know, whatever. It's going to be added, right? So we just say, and in fact, you know what? We'll just do it. I won't even do it there. I'll do it over here. I'll do it at the end. So we're going to come through here. We're going to do our point index sum twice. Total source light, total desk light. Like, I just go, okay. I sum up the total source light and the total desk light, and I see how much light we have, and I just make them, they have to be the same. Just throwing it out there as a really dumb idea. So I say, okay, my source emit C and my dest emit C, I've got. So you see where I'm going with this? So I then know the ratio of these two things. So assuming that my source sum is greater than 0, which it always should be if there's any light in the scene at all, right? The other thing too is the moon here is not really getting totally accounted for. So I mean, maybe I say that this starts with moon color. I don't know, right? So you know, let's sum power times the moon color there. I don't know. This is again very, very stupid, as I said before. So then when we come through here, we just say, all right, look, we're just going to go ahead and we don't even care about the subtraction part. Like, it doesn't matter or something. We don't care what happens there. We do our remove C value. We don't have to worry about the clamping because we don't have that removal coefficient here. So this doesn't happen. So all we do here is say, look, we know that we want our sort of our normalization ratio, right? Our normalization for the color. We want the dest sum we want the dests, we want to bring ourselves back up. Actually, so how do I want to do that? I have the total, I want it to equal the previous. So actually this is backwards. Right, so I have a destination, I want it to equal my source, so I'm just going to literally multiply when we come through. I'm just going to literally multiply the dest emit C by the normal coefficient, and that's just how we're going to restore our light amount. Period. Again, I have no reason to suggest this is a good idea. It's probably not. I'm just going to do it anyway because I can, right? So this should, in theory, renormalize our lights so that we can't add light to the system. Of course, it doesn't seem to be working, but it should, right? Did I get that right? I'll leave out the moon color for now. So I feel like that should be keeping our light from expanding like it is, and yet it isn't. Let me go ahead and step through that. I'll see what that's doing. Sorry, I know we're supposed to be done, but I want to see what happens here. Very interesting. So we do just have a bug here. And I guess that's the amount of light that's being put into the system. So let's take a look at this just one other way. What if I simply said the source sum was fixed to a particular value? So you could only have a certain amount of light in the scene. Again, just making this up as I go. Don't know how much light should be in the scene. Not sure why that would have created such an odd effect. Unless I'm just too low. Seems about right. I don't like how spiky these numbers are. Like, those are just really high numbers. Way too high for floating point really to be. Sadly. Let's get a little more light in there. It's basically exposure control in a sense, right? We're basically saying like, okay, there's going to be a certain amount of exposure control here. playing around with that moonlight. It's certainly interesting. Gotta make sure I fix make the lighting volume properly track the camera. It's currently room-based, which is dumb. That's why I get that white flicker over there. It's really weird the way the flickering still works. I don't know. I'm still not willing to believe that we don't have some issues here. I wonder if that's just because our light max values are too high. Because again, the total amount of light, remember, is supposed to be being clamped here. Right? We're forcing it to be a particular value. And in fact, I suppose I should be able to actually double check that. There's a thing that we can use to check the destination light as well. All right, let's play with this value again. It's weird, you can actually see that exposure control, like it's actually sort of changing the overall brightness. That's pretty bizarre. Let me go and change that moonlight back. Now all the lights are max power 1. Yeah, I don't know. I still think we've got issues. And I'm just not quite sure yet. So we'll see. But we got to play around with it a little bit. I'm gonna see what happens if this value is made, you know, something not 10, basically. Yeah, and so you can see that, like, I guess one of the problems is on every frame you will concentrate the light concentration at the actual light source becomes quite high because not very much of it is coming out. And so when you sum up all of that transmission amount, you end up counting for mostly the light that's in the light source, right? It's interesting. So I think, yeah, I think we're like maybe one more sort of transformation away from having this working in a way that we can use reliably. I think we just need to go over how we want to transfer light between the surfaces and get that dialed better. And again, the idea is to slowly diffuse the light over time while not adding or removing light from the system in a way that produces objectionable artifacts, right? And part of the problem there is we have the concept of an emitter, which is something that emits light. So we'll also need a concept of something that takes light away, right? And so I think if we just kind of balance those out, and by doing it bidirectional, which I think I'll do tomorrow, I think we could do that because the skylight would take light away. And in general, that transfer takes light away. In theory, I think we can get something that allows slow transmission, but still actually works, right? So we'll see. What comes after lighting? Any ideas? After lighting, we're gonna go clean up the game code. Since now we kind of know exactly what needs to go on in there, we're just gonna go in and make it so that, like, you know, add some nice controls and like basically allow you to kind of play through a bit. And sort of in tandem with that, we'll probably do some. We'll clean up the art asset stuff so we can put in some real art assets. Just gotta basically start on game stuff, game passes. The current code base is pretty manageable. It's not that big. There's a clock. We had a clock program, but I don't know that it's installed on this computer when I change computers. I can go grab that. I'm going to leave that up because I would like to read that paper. I don't know what that means. Does that mean SourceForge is down? Here we go. So I don't know if this is installer or not. I'm assuming not. But it might be. Nope. So we should be able to do it. So there you go. I think that's accurate. Probably. Possibly. John wants to know if I can work yakety sax into the program somehow. The question is not whether I can work it in, but how I would avoid the copyright violation and imminent lawsuit, right? Because I think we all know that Handmade Hero, once it is released on Steam, will make like literally billions and billions of dollars, right? And so the problem that you're going to have there is that then the people who make yakety sax are going to come and take all the money, right? So the question is just, how do you solve that problem? So if, John, you wanted to purchase the rights to yakety sax and then donate them to the Handmade Hero project, I feel like that's totally acceptable to me, and we would integrate it in after we receive that. Nate change one note like Vanilla Ice did, or Ray Parker Jr. would be the other one to look at. I feel like Handmade Hero could feature a suite of Huey Lewis in the News modified songs. Right? All right. I'm going to go ahead and shut down. All right, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you want to follow along with the program on the stream, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can follow along at home, just like picture pages. If you were a kid and had picture pages. Anyway, I will be back tomorrow when we'll take a look at changing the light transfer there, because it's mostly where I want it to be, but we just have to get a little bit more rigorous about the math of the lighting transfer before we can actually use it as something that's valuable and useful and contributory to the game. That's about it. I will be back here tomorrow, so hope you will join me for that. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.